This is the third short video in our lecture on study design and analysis in epidemiology. We will briefly discuss error, bias, and confounding and how to deal with those, and briefly talk about differences in statistical and dynamical models. Even perfectly designed studies may not provide you with the true number of the measure or effect you are looking for, and in most studies the true number is hidden underneath some bias and random error. Random error is typically introduced because we're not including the entire population in our study, but some representative sample. The smaller our sample size, the more random error. We want to include enough people in our study so that our measure of effect is believable and not masked by random error. We use statistical approaches to assign probabilities to our findings, being a product of random error rather than a real phenomenon. Bias is the difference between observed value and true value due to all causes other than random error. Unfortunately, bias does not go away with greater sample size, but needs to be dealt with during study design. There are different types of bias, such as selection bias, which is error due to systematic differences between those who take part in the study and those who do not. For example, if we want to measure prevalence of a disease, we should not be enrolling participants at a health facility, because people accessing care is more likely to be sick than the general population. Information bias is a flaw in measuring exposure or outcome data that results in different quality or accuracy of information between comparison groups. For example, if you ask a person how much time they spend on their phones every day, this might result in very different numbers than estimated by a screen time tracker app. This image is often used to describe survivor bias. During World War II, this plane came back to the army base when most other planes were shot down. The red dots show where the plane was hit by bullets. The engineers thought that it would be wise to make the plane stronger where the bullets hit. One clever statistician considered all the data of the planes that came back, and noted that this plane could still fly with all these hits, and that it is likely that the planes that were hit elsewhere didn't survive to come home. Those spots probably needs the enforcement more than these red dots. Another example of survivor bias, more relevant to infectious disease. Say a clinical epidemiologist is interested in quantifying side effects of TB treatment. If you ask TB survivors about their TB treatment side effects, you may get a biased picture of the truth, since those who did not survive may have had a different experience. This is a tongue-in-cheek example of non-response bias. Please pause to read this very self-explanatory example. Also recall the 1936 presidential election from the Thinking About Data lecture. The best way to avoid bias altogether is by choosing the correct study design and enroll a representative randomly selected sample of individuals. One can adjust for some biases during study analysis by using weighting methods or sensitivity analyses, but it's very important to clearly communicate potential biases in your study and the limitations that imposes on the interpretation of results. Another problem that plagues inference from epidemiological studies is confounding. I won't give you formal definitions, but explain it through this simple example. A cross-sectional study found a strong association between literacy and HIV status, with a prevalence ratio of 3.67. One can argue from this evidence that illiterate people are more likely to acquire HIV. Could there be a hidden reason that we observe this association? Pause the video now and think about this. What if some of the study population were much younger than others? If we break the data down by age, we see that prevalence ratios for 6 to 15-year-olds and for 16 to 24-year-olds break down to 1, implying no association between literacy and HIV status within age groups. Rearranging the tables in the previous slide, we can see that in this study, literacy increases with age and HIV prevalence increases with age. And all this evidence shows that age is a confounding factor for the relationship between literacy and HIV status. How do we deal with confounding? We randomize participants to intervention groups to make sure that our intervention and control groups are similarly representative of all known confounding factors. Or we can restrict participants to only one group of the confounders. For example, only enroll adults in the previous example. We can also deal with confounding through our study analysis by doing multivariable modeling that statistically adjusts for the effect of one risk factor given the presence of a confounder. We can also do stratification during study analysis and conduct separate analyses for each level of the confounder. So far we've discussed basic epidemiological concepts. This lecture is of course part of a clinic on meaningful dynamical modeling of epidemiological data. So I would like to tie things together and briefly compare and contrast statistical models and dynamical models. In order to do descriptive and risk factor analyses from data collected through epidemiological studies as described in this lecture, we make the implicit assumption that the individuals we sample are independent of each other. Dynamical models focus explicitly on the interdependence of individuals. For example, we explicitly model the transmission of disease from person X to person Y. We briefly discussed how statistical models can account for random error and bias in data to assess relationships and find correlations that may imply causality. In dynamical models, we explicitly model or hypothetically declare specific mechanisms or associations to explore the interactions. In this course, we'll show you how to develop dynamic models in a data-driven, probabilistic framework that allows us to account for dependence, random error, and bias, while linking patterns at multiple scales. We can use our example question from this lecture, is male circumcision effective against HIV acquisition, to illustrate how patterns can be linked across scales. We measured at the individual level in our RCT that male circumcision reduced risk of HIV by 60%. We can use this finding to answer a research question at the population level. By how much would HIV incidence decrease if we circumcise 50% of all men? This latter question is a question that is only suited to answer through dynamical models. So in summary, epidemiology seeks to measure and understand the causes of disease. Epidemiologists conduct observational and experimental studies to obtain data and measure things like incidence, prevalence, risk ratios, odds ratios, incidence rate ratios. Epidemiological studies are subject to bias, confounding, and variability. And traditionally, the focus is on discovering correlations that may lead to identification of causal factors. Dynamical models informed via epidemiological studies can answer questions that traditional studies can't. We would like to thank our funders and collaborators that enables us to put this course together.